Hello AP Chemistry and welcome to 4.4 Redox. So, for most people, this is probably the most challenging section of Chapter 4, and it is the section where, so going back to acids and bases, I said you have to memorize those strong acids and bases because every time you assess a question, you have to know if it's a strong acid or strong base in order to answer the question correctly, right? Likewise for redox, those rules for assigning oxidation states of the utmost importance that you memorize them, right? So that way, every time you're asked, is this process redox? Or what is oxidized and what's reduced? Which shows up a lot on free response questions because it's one of those easy questions you can throw in regardless of what the topic regardless of what the theme of the question is, just to check this one point, right? So please make sure you memorize those rules and that you can use them in every scenario. So this section, again, just like with the acids and bases, how it's a small introduction to something we're going to expand on later, right? Same thing. So here we're going to talk about the concept of oxidation and reduction, right? What does it mean? What are some ways we can see it or think about it at the micro and macro level, right? And then there's another unit later, right, that expands on the topic and talks about the applications of this and why this is such an important thing. But for right now, it's important that we talk about our definitions, right? So when we say that something is reduced, right, we say that it gains electrons, right? Which also means that in terms of its oxidation state, right, its oxidation state is more negative. And we want to be mindful with our wording here because more negative actually means smaller. So we don't want to use the word bigger because that would be inappropriate, right? Because it's actually smaller. So make sure that your words are clear. So I always say that the oxidation state becomes more negative, right? And if we're talking about an oxidation process, right, then we would lose electrons and our oxidation state is more positive, okay? And note that it doesn't say becomes negative or becomes positive, right? Because becoming more positive can mean going from +2 to +4, right? And that's an oxidation, right? Or oxidation could be going from -5 to -2. Also oxidation. Yes, does that make sense, right? So I think the wording here is very important. This is how I memorize it because it makes sure that when I apply it in any scenario, I'm going to come up with the right answer, okay? For those of you that like little, like little weird things to help you memorize, right, there is the Leo says grr, right, where the loss of electrons is oxidation, gain of electrons is reduction. People like those things. I would just as soon memorize these definitions and call it a day. That's just me. To each their own. Okay, and then your book goes and gives you some examples, right? So here we have the oxidation of copper, right? Here we have the oxidation of mostly iron, right? And here we have the oxidation of silver, okay? So when we think about the oxidation of all of these, note that we are starting from the actual metal itself, right? Pure metal, which has an oxidation state of ding, 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 0. Things in their elemental states have oxidation states of 0, right? So when we say they're oxidized, they turn into their ion form, right? And when we say they turn into their ion form, right, it's not just like free copper ions floating around, right? We're talking about having gone from elemental copper to a copper compound, yes? And there's a whole world of copper compounds that it could form, right? Depending on what the environmental conditions are for copper anyway, right? Right, it goes from being an element to a compound. And metals always become cations, right? That's what we've talked about since last year, right? Metals will tend to lose electrons in reactions, right? They become cations. So then on the flip side, when we ask things like, can a metal be reduced? Your answer is no, right? Metals are not reduced. Metal ions can be reduced, right? But a metal can't be reduced, right? And note that in common use, when we say, oh, that, when there's like a rusty shovel or something, I don't know, in your garage, right, you might say, oh, it's been oxidized, right? And when we use that in common language, we often mean that it's reacted with oxygen in the air, right? And that is a common thing, right? In that if I took Fe metal, right, if I took Fe metal, and if I react it with some oxygen, right, yes, the resulting compound, right, means that metal was oxidized upon reacting with oxygen, right? But note that oxidized doesn't always mean reacts with oxygen. Yes, just in a common use way it sort of does. All right. Moving along. So here we have a whole bunch of the examples from your guys' book, right? Where we have calcium is allowed to react with some oxygen gas, right? And here we have some magnesium metal reacting with some HCl, and here we have copper metal reacting with silver nitrate. In every single one of these, at least one of the reactants is an element, yes, is a pure element. Pretty much that's going to always be one of your giveaways, right? If a pure element reacts, it is definitely redox, yes? If a pure element reacts, it must be redox, right? Because it's going from an oxidation state of 0 on the reactant side to a compound on the product side where it's going to have some other oxidation state. Yes, does that make sense, right? So that's going to always be one of your giveaways to look for, right? In addition, right, property changes, right? Like this is one we sort of did last year where we used magnesium, right? But if I take a metal plus oxygen and I get an ionic compound, the properties are vastly different, right? We could take a mallet to this and crush it, and it would become this fine powder, right? Versus the malleable metal that it was before, right? Here, right, when we take our magnesium metal, right, at the end, right, we end up with this ionic compound that we could isolate, right? Which, again, very different than before. Here we have hydrogen ions, which become hydrogen gas. Again, very different properties than before, right? So just things to be mindful about, okay? And something to tuck away. Note that all these redox reactions happen, yes, right? As in we put magnesium metal in hydrochloric acid, and I know that sounds weird and ridiculous. Don't mind the dog. Magnesium metal goes in here, and the reaction happens, yes? Calcium is exposed to air, and the reaction happens. Copper wire is put into some aqueous silver nitrate, and the reaction happens to form product, right? Which means that the reverse reaction does not happen appreciably, yes? Does that make sense, right? The reverse reaction does not happen appreciably, right? Tuck that away and hold on to it. We will need it later. All right, activity series again. So this again, all the everything here in this section 4.4 about redox is an introduction. Later on, we're going to put some numerical values on this activity series, and we're going to change what we call it, right? But here, this just tells us what things are easier to oxidize, right? So here, what this is telling you, lithium is the most easily oxidized, right, of all these metals, which should make sense because lithium also has the what? Ding, 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 lowest ionization energy. Yes, as in it is the most easy, it is the easiest element to remove an electron from. Oh my gosh, which is exactly what this table is talking about, right? The ease with which you can remove an electron from something to form a positive ion, right? So lithium is the easiest, right? Gold then is the hardest to oxidize, yes? Gold is the hardest to oxidize, which then on the flip side means that lithium is not readily reduced, yes? On the flip side, what that means is lithium is not readily reduced. So thinking back to what we just said, this reaction, right, is unlikely to go in the backwards direction. Yes, lithium ions are unlikely to take an electron and become lithium metal, right? Does that make sense, right? Where gold, if we had aqueous solution of gold ions, they will quite readily take those electrons and go ahead and form some solid gold, right? Does that make sense? If we were to read this table in the backwards direction so that we could talk about reduction. All right, so in your guys' outline, I put these few examples in there just because it's good to do some other examples, right? Because the concept of redox applies as long as we have those definitions, right? So let's go ahead and run through these. So applying our rules. So obviously elemental state 0, right? Here, we're going to use our rules which say that hydrogen is typically +1, right? Which then means, so if this is +1, what must chlorine be to make it be 0? -1. Yes, does that make sense, right? All right, which then in terms of is it redox, right? We have chlorine going from a -1 and then chlorine going to 0, which means that chlorine is, right, so here we have an oxidation, and we have hydrogen going from +1 to hydrogen 0, right? Which means that this one is a reduction, yes? Now, what that would mean is that hydrochloric acid undergoes a redox process such that chloride ion is oxidized and hydrogen ion is reduced. Yes? Okay. Moving along, here we have oxygen element, and then applying some rules. So oxygen has a rule, right, which says -2, which means that the total is -4, which means that carbon must be +4, right? Here, they both have most of the time rule. So if this is +1, then we have a total of +2, which means that oxygen must be -2. And the way I like to do it is that I put the oxidation states up here, because the oxidation state is for the individual atom. And down here, I just put my sums, right? So like my work thing, right? So if I have 2 hydrogens, each with a +1, +2 would be the sum, right? If I have a -2 and I have 2 of them, -4 is the sum, right? That's just how I like to do it to keep my math easy to interpret for me, okay? And so here, hydrogen typically is typically +1, right? Which means this is +4, which means that this has to be -4, right? So then what we'll see, right, is that we have methane, and our wording that we would use is methane is oxidized, and we would say that oxygen is reduced, okay? And whether you wanted to say here to here doesn't really matter, right? But oxygen is reduced and methane is oxidized, okay? Now, if we were asked like what atom, then we could say carbon goes from -4 to +4, right? But if we're asked for like which species is oxidized, we would say methane. Yes, does that make sense? Because carbon doesn't exist separate from methane, okay? Do be mindful, right? We could also talk about oxidizing agent and reducing agent, which is an older terminology, which you might see sometimes. And when we say that something is an oxidizing agent, right, it is the thing that allows something else to be oxidized, which means that it takes electrons, yes? Which means that it, in and of itself, is reduced. Does that make sense? I sure hope so. Make sure you review that. And like I said, please memorize those oxidation state rules because we will use them all year. All right. Thank you for listening. Be good, and I will see you soon.